Okay. Hey, ladies and gentlemen, why don't you find this right here? Uh, this is kind of exciting. Today we finally made it to the ladder problem.
Literally, I was up all night.
You got to go a little backwards in the packet. Yeah, a little bit. It's one that looks like this.
Where? I can't. Oh, here we go. It's like in the way beginning.
Let's see. When I was in college, I didn't take calculus until I was in college. I didn't take it in high school. When I was in college, I did the ladder problem. My father did the ladder problem when he was in college. My father's father did the ladder problem when he was in college. My father's father, I think, only got through the 7th grade. But if he had gotten to calculus, I'm sure he would have done the ladder problem. This one is like a classic. Everybody does this one. So here's the setup. You got a 20-foot ladder. Are you guys comfortable with ladders? Can you go to the top of a ladder? Or are you afraid of?
No. That's my dad's job.
That's my job at my house, and it terrifies Julie. She I cleaned the gutters out on Tuesday, and she stood like just near me, watching anxiously, like not in a position where if I fell off the ladder, she was going to be able to help, but just there to make everything.
Yells at my sister and I to go do that. Like the exact same thing. Just
Mhm.
stand there.
Just stand there
I'm
and
like, I have homework. She's like, make sure your dad doesn't fall. Hey.
well, it's good not to fall. But she wasn't even standing at the bottom where she could like steady the ladder if I started to fall. She was just too nervous to go inside, but not comfortable enough to stand under the ladder. Anyway, ladders, very scary. Very scary stuff. So you got a 20-foot ladder, and the length of the ladder is not changing. That's fixed. That would be fixed, right? Give me a right on that one.
Right.
You're not going to change the length of a ladder. Okay. And let's suppose that this ladder has been leaned against a wall. So here's a wall right here. And let's also say that it's starting to slide. And so it's sliding such that this side of the ladder is moving away from the wall. And the problem says that it's moving away such that the rate of change of this side length of x is equal to 2 feet per second. And that's constant. Here's the question. This is the ladder problem. Well, one, what's going to happen to the top of the ladder? It has to move down, doesn't it? We know that the top of the ladder is going to move in this direction. The question is, at what rate is this side going to move down? Is it going to move down at the same rate that x is changing? Is it going to be constant? Is it going to be speeding up? Is it going to be slowing down? What's going to happen to the rate at which this ladder slides down the wall? That's what we want to know. You guys have the idea of the problem? Okay. So here we go. Here's how you solve one of these. This is a related rates. Step number one is you have a triangle. On this triangle, you have 3 sides, y, x, and 20. You need to cook up an equation using y, x, and 20. And I'll give you a hint about how you're going to write that equation. It rhymes with Pythagoras. For those of you at home, they're chewing on it. They're thinking about it. Who can tell me an equation that we can write that would relate x and y and 20 and would apply this fellow whose name rhymes with Pythagoras?
Is it Galileo?
It is not Galileo. No, it's not. It's not him. Naranjan has an idea. X squared plus y squared equals. How'd you get the 400? Beautiful. Nice. Okay, so that's step one. Step number two is we're interested in the rate at which y is changing. So we're going to take the derivative of each one of these parts with respect to time. Now, if you take the derivative of the first part with respect to time, that's going to be a chain rule. Boom, boom, boom. Start with the outside function. The outside function is something squared. Hey, folks, what's the derivative of something squared? 2 times something. Cool. Multiplied by x is changing over time, isn't it? Look at x. X is getting bigger as time goes by. Are you with me on that? Give me a nod. Okay. So since x is changing over time, we have to multiply by the rate of change of x over time. So this is a chain rule where you think of x as an inner function. We good with that?
Yeah.
All right. Next one's exactly the same. The derivative of y squared over time would be 2y times the rate of change of y over time. And on the other side, don't overthink this one. As Naranjan pointed out to us, 20 squared is just 400. What's the derivative of 400? Okay, so there's our equation. From that equation, we are interested in figuring out the rate at which y is sliding down the wall. And that's dy dt. So we want this. I'm going to take that equation and I'm going to solve for dy dt. And the first thing that you would do is you would move this out of the way. You would subtract this over. So if you subtract this, you would get 2 times y times the rate at which ladder slides down wall is equal to 2 times x times rate at which ladder slides out. And then we're still trying to get this by itself. If we want to get this by itself, what do we have to do with the 2y, folks? Divide. So let's divide by 2y. Let's divide by 2y. The rate at which the ladder slides down the wall turns out to be equal to the distance it is from the wall multiplied by the rate at which it's sliding out over its height on the wall. So there's your equation. Now the question was, how does this change as we move on down the wall? And so I'm going to give you 2 times. Let's start with, let's see, can I zoom this out a little bit? Let's start with when x is 1. When x is 1, the ladder's pretty high on the wall, isn't it? Give me a yes.
Yeah.
This is 1. This is going to be pretty high up. So right here, I'm going to say dy dt is equal to 1 is our x value. Dx dt was given to us. It is a constant. What is the value of dx dt, everybody? It's given to us as 2. So I'm going to plug a 2 in right here. That never changes. Now, we were not given the y value at this instant, but couldn't we figure that out? Anyone have an idea how we could figure out the y at this moment? Yeah, that guy whose name rhymes with Schmythagoras. If you know this is 1, and this is 20 right here, and this is y, wouldn't you just have 1 squared plus y squared is equal to 20 squared? So y squared would be equal to 20 squared minus 1 squared. What's that equal to? $3.99. One of my favorite prices. So y would be equal to the square root of $3.99. All right. So how fast is the ladder sliding down the wall? Here we go. 1 times 2 divided by... You know what? I just realized I made a very small boo-boo. Did anyone, you figured it out. What am I missing?
You forgot the negative when you minus 2x.
I did. Everyone see that? That right here when we subtracted, we're going to get a negative. All right. Good catch, Jen. Was anyone else wondering about that? You guys are so nice not calling me out. That was very sweet. You should definitely call me out on something like that. All right, so there's a negative here and a negative here. And that would also put a negative right here. And the negative kind of makes sense, doesn't it? Like it's sliding down the wall. The length is getting smaller. So that would be weird. There is an extension of the ladder problem where the ladder is changing size. They do it in BC. It's complex.
Why would you have a ladder? Realistic.
Oh, it's not realistic. It's just a brain bender.
You know, what if one of those trucks with like the ladders? Like, the truck's moving away the ladder. The truck's moving away the same time the ladder is like extending out.
It's like an extension ladder.
Yeah.
The one that they do is really weird because the ladder starts really small and then it gets bigger and then it gets smaller again as it moves.
It's a magic ladder.
Wait, where did you get
Don't think about it too hard.
Where'd I get the negative? We realized that I made a boo-boo up here. I should have subtracted. I was subtracting. So when I subtract, we get a negative on this side. That's where the negative came from. Okay, so at this instant, it was sliding down the ladder at a rate of 0.1 feet per second. Here's what I want you to do. I'm giving you a different time. Now let's suppose that x is 15 feet. So at 15 feet, the ladder is way out here. Y is going to be a lot smaller. I want you to figure out how quickly it is sliding down the wall at that instant. It's just a matter of applying this same formula. Okay, so I'm going to give you about a minute. I want you to plug that in and see what you get. I got a square root of 175 in the denominator this time. Does that agree with what you guys got? Anyone not sure where I got that from? It's y squared plus 15 squared is equal to 20 squared, and then solve that for y. So we just changed what the x value is, solved for a new y. So that gave me this. So the ladder actually is speeding up. It's sliding down the wall faster than it was right here. Yeah, it's accelerating. It accelerates wildly too. At the last instant before it hits the ground, it's going infinitely fast.
Yeah, it's kind of just gravity is more an effect than gravity.
Yeah.
Also, as the y gets smaller in the denominator, you're dividing by very tiny numbers, makes it big. Okay, so there it is. There's your ladder problem, folks. Flip the page, and let me first tell you that this is problem type number 1, which is Smythagoras. And then I'm going to show you problem type number 2, which is on the next page. A what?
Is it like a train problem? That's what it's always
Do you ever see Direct?
Oh, yes, we will do that. Except for, I think we end up doing it with like starships in like a
Mickey Mouse.
Star Wars context. All right, I'm going to be quiet for a second. I want you guys to read number 2 to yourself.
Why is he shooting?
I didn't want to kill a bird.
He's practicing.
You could have done a clay disc.
I could have.
Listen, it's called practice.
Well, it would be more realistic, but it's harder to draw a clay disc than a balloon. I'm good at drawing a balloon.
It's practice.
Okay, fine. I'll tell you what. What do you want it to be?
A balloon.
You want it to be a balloon?
Yeah.
Okay.
A clay balloon.
It's
A clay balloon.
It's Gail's balloon.
Okay, hang on.
It's Gail the clown's balloon.
Okay, now it's a clay balloon.
That's why Gail is
He's taking clay balloons that just drop to the ground.
Okay, is there any other context that I failed to include here? Oh, okay. He does need a name. Would you look? Was that you asking to name him, Franny?
Can it be Gail?
Gail number 2.
Gail's mother.
Gail.
Wait, it should be Gail Jr.
I like that the brother would just be named Gail number 2.
His parents are really
Gail
fair.
Senior.
It would be very confusing to name the second child Gail Senior and the first one Gail Junior. That would.
An older brother.
No, this is his younger
This is my older brother Gail Junior. This is my younger brother Gail the third. Okay, so first things first. In this problem, it says how quickly is his angle of elevation changing? So we figured out that he is raising the gun in order to. What are you doing on your phone? He is raising the gun like this in order to follow the clay balloon, which is somehow, despite the properties of clay, floating up into the sky. So this angle is changing. Are we good on that? So we now need to write an equation that relates the angle and the height. And this one is not going to be Pythagoras because there's an angle involved. And if there is an angle involved, it is time for my buddy trig. That's what trig is for. Trig takes angles and turns them into ratios. Trig is his much younger brother.
Are you sure it's not? That's not Pythagoras.
Sure it's not Galileo.
I don't know what to think anymore, to be honest. So look at these two sides. This one right here would be the opposite. This one right here would be the adjacent. Opposite and adjacent, what kind of trig are we looking at here? Okay, so step number 1 on this problem is tangent of angle is equal to opposite over adjacent, h over 25. And do yourself a favor, you know you're going to be taking the derivative of it in a minute. So just multiply both sides by 25. The height of the clay balloon is equal to 25 times the tangent of the angle at which Gail number 2 holds the rifle. Okay. Step number 2 is to take the derivative with respect to time. Start with this. If you take the derivative of the height as time goes by, you get dh dt. On the other side, you are using the chain rule, where the angle is your inside function. So you're saying the derivative of the outside is tangent. Oh, I think we started class with this today. What is the derivative of tangent, folks? Good, good. So 25 secant squared theta multiplied by, since the angle is changing, what am I going to put right here, folks? D theta d time. Don't hate on theta. Theta is a letter, just not in our alphabet. Yeah. It is, yeah. It's their T. It is. Alpha, beta, gamma, those are all letters in their alphabet. Okay, so we're trying to find how quickly Gale number 2 is raising the gun in order to hit the clay balloon. So we need to solve for this, which means that we need this value and this value. Were we given the rate at which the clay balloon is rising? What is that equal to? Okay, so step 3, plug in an 8 right here. On the other side, secant squared of, were we given the angle at the instant that we're interested in? We weren't? Oh, ew. What were we given instead? We were given the height. All right, so if we're given the height, how could we come up with the angle that has to go right here? $25 is right here. Angle is right here. They told us the height at this instant is 40. I'm getting serious inverse trig vibes from this problem. Are you? Are you feeling it? So if you want an angle, that's where you use inverse trig. So you're going to say inverse trig of 40 over 25. So let's get that number. Mode, I'm in radians. Inverse trig of 40 over 25 gives us one of my favorite numbers, 1.01. I don't know. It's a palindrome. It's the same forward as it is backwards. That's pretty fun. Okay, so now we're over here and we are solving this equation. Boop, boop. And I need to put this in the calculator. Since we don't have a secant button, what are we going to do instead? We're going to, I mean, we could cry. That's an option. Tuesday, I don't know if that's going to get us the right answer. See how I'm going to divide by cosine? Dividing by cosine is what you do when you're asked to multiply by secant. So this side would be equal to 88.999999. We'll call that 89. So 8 is equal to 89 times d theta dt. Therefore, the rate at which he raises the gun is equal to 8 divided by 89, which is, I want to throw that in the old calculator, 0.09, and that would be in radians per second. It's pretty fast. Okay, so that's your second kind of triangle problem for today. How do you know when you need to do a trig problem? The answer is anytime that you have an angle. So you got 3 sides, Schmidthagoras. You got an angle, trig. Angle, trig. Sides, Schmidthagoras. Schmidthagoras, sides. Sides, Schmidthagoras. Angle, trig, trig, angle. There's one more. Now the good news is I saved the easy one for last.
Your drawings are like kind of good.
Thank you.
Is that good? I feel like you always hate on your drawings.
What was that?
I feel like you always hate on your drawings.
I hate on my drawings?
No.
I don't think I hate on my drawings.
I think it's
I'm really a big fan of this one. It's a light bulb, and it's a what do you call that? A lamp post, and I drew the light as a giant light bulb. I think that's cute. In fact, I'm gonna color it in with a little yellow just to doll it up. All right, take a second to read the problem to yourself. Well, no, it actually tells you this person's name is. Well, it says it's a cool dude.
Yeah, Gale number 3. coolest of them all.
All right, so this is Gale the third. It does sort of look like Waldo's shirt, doesn't it? I'll give it Waldo's hat too.
Gale the third is secretly where it's
It's like, find Waldo's shadow. So the problem asks us to figure out how quickly is the dude's shadow growing. So can you guys picture that this is his shadow? The light is shining down, leaving a shadow on the ground right here. So that would be shadow. And what we're looking for is what is the rate at which his shadow grows as he walks. Have you guys ever done that? I used to be obsessed with this when I was like a little kid. That when you would walk under a lamppost, like your shadow would get longer and longer and longer the further that you walked. I don't know why I found that so interesting, but I would just stare at my shadow as I walked. Anyway, it grows as time goes by. And the question is asking you how quickly. The trick on this one is to see that there are two triangles. Do you see the two triangles? Okay. So the first one looks like this. Okay. So there's little triangle. And on the little triangle, we know the ratio of the two sides is 5.5 to S. And then here's the big triangle. Ba-boom, ba-boom, ba-boom. On the big triangle, the ratio would be 10 to this distance. Now, this distance is not S, and it's not X. What is that distance right there, folks? Okay. So the way you're going to do this one is you're going to set up an equation using the fact that these triangles are similar. They have the same ratio. So I'm going to write it this way. S is to the 5.5 as the long side, as S plus X is to the 10. And this, by the way, is your third kind of triangle problem, and it's called similar triangles. All right, moving along. Our goal is to figure out the rate at which the shadow grows. So I'm going to take this equation and I'm going to solve it for S, which is not too hard to do. You get to cross multiply. So 10 times the shadow is equal to 5.5 times the shadow plus X. So 10S, that is an S, not a 5, is equal to 5.5S plus 5.5 times X. Again, we're solving for the shadow, so I want to get the shadow by itself. Subtract 5.5S from both sides. You get that 4.5 shadows is equal to 5.5 X's. S is equal to 5.5 over 4.5X. Now, I know I flew through that like a crow through a cornfield, but I think you guys know how to do that sort of equation solving. So now, here's the part that's new for today. You got to take the derivative. Okay, finish strong. When I take the derivative of this side, of S, what am I going to get? The rate at which the shadow grows is equal to, the other side is really, really simple. Just ends up being the coefficient times, since this is to the first power, its derivative would just be dx dt, or 1 times dx dt. So we would get our answer just by plugging in dx dt. Wasn't that given to us? This is where you guys say yes. It was. It was. What's it equal to? It is. Okay. So this would be 4. We plug that into the old calcuma thingamajigger, and we get a number. And that number ends up being 4.9 feet per second.
So, will we have a calculator on this test?
Yes. Is that exciting?
I just feel like I've been so calculatorless.
Deprived. Yeah. You two are going to need a little time to get reacquainted,
Yeah,
reconnect.
I forgot.
It's this button right here.
Are you sure?
I'll check. It worked. All right, that's the game, folks. That was a lot. That was really a lot. Turn to your neighbor. Say nice work.